gray hair or brown hair? Okay, gotta keep. Hello, Ty. Are you in group A for the lab? Or do you have a microphone? Actually, you could, if possible, chat.
I believe so, but I'm not sure.
Okay. Are you usually here most days?
Yes.
Okay. Yeah, so I don't know which one of your team members sent me your prediction for the angle that you had. I think yours was 34 degrees or something. But was that you, Solo, or not?
Yeah, that's me.
Okay, that sent the prediction?
Yeah, both times.
Okay. Anyway, you guys nailed it. um, let's see. I sent a message back to you with a picture of where it landed, but the measurements where it landed, you have to add 13.3 centimeters to because it's measured from the point directly underneath the counter edge on the floor. And when you add those 13.3 centimeters on there, the data points will end up being either side of where you predicted it to be. So you're off by like, I don't know, 1 part in 400 and some. Actually, if you calculate the average, it may be really tiny, just a tiny variation from what your prediction happened to be. So I think you're going to get the extra points for best prediction so far. I've got 2 teams I haven't even heard from yet, but at least I think I sent their angles to them, but that's all so far. So today we're going to start into some of the chapter 5 material, which is looking at introducing friction into Newton's second law problems. And it's well, it adds a complication, but it's something that you have to consider. And so we don't usually have friction-free situations. So I'll jump over and share the screen so we can see how to deal with that. And should say friction here. Now, the idea is that if you have 2 surfaces next to each other and you have those things slide past each other, in this case it would be a calculator on a piece of paper, there's a force that opposes that motion, and that force is what we call friction. Now, this may appear to be pretty smooth on the bottom, and you'd think that the paper will look to be pretty smooth. But if you could look at this under a very high magnification, and for high magnification, if you really want it, you'd have to use something called an electron microscope. And so you'd have that being the case. But anyway, you can look under very high magnification, and what you would see is that the bottom of the calculator is not smooth, but it's got all kinds of bumps and wiggles and things on it. And the same thing with the top of the paper. It's not perfectly smooth. It's got a whole bunch of bumps and wiggles on it, and I don't have them overlapping here, but if they were, if there was a pressure from above, and that'll be produced by the weight of the object that's on top actually, then you can have these bumps and wiggles interlocking a little bit. And when it's at rest, they'll just be sitting there interlocking, but to get it to move, you have to push it sideways, and you'll actually be breaking off a little bit of material from both the surfaces, just a few atoms worth, but after a while it starts to show up. And you see evidence of that with, for instance, skid marks on a road when you've got a hefty car that's sitting on top of a rubber tire and that thing skids, then it leaves some of the tire material on the road and might acquire a little bit of the road material as well. So that's the basis of friction, is that it's due to this bumpiness and interlocking parts and things like that. Now, it's absolutely impossible to calculate it on a point-by-point basis. So the atoms in this peak are going to be opposed by the atoms in this little bump that's on the top surface and stuff like that. And there's no way that you can deal with that. But you can find out that experimentally the frictional force will usually be about some particular value. And what we've found is that the frictional force is proportional to the normal force. So now we haven't talked a lot about the normal force yet, but the normal force is if you have some object that's sitting on a surface, so this could represent a tabletop, and you have something there, and if you look at the forces that are acting on this, could just be a box, could be a book, could be anything, doesn't matter what it is, but if you make a free body diagram for that, it would have mg pulling it upward, or downward, I mean, and then there's a force that opposes that because the mass doesn't fall through the table, and we call that force the normal force. Now, that normal force is due to the repulsion of the atoms in the bottom of the mass. They're being repulsed by the atoms in the top of the tabletop. And if you try to push them together, you can't push it through there because those atoms start to repulse each other. And we don't try to do that on an atom by atom basis either. We just say, oh, that's the normal force. You add all of those little repulsions together and you get something that matches the weight of the object. And so it doesn't fall through the tabletop and it doesn't jump off the tabletop. This normal force, most of the time, just matches the weight, at least on a horizontal surface. That's not the case if it's tilted, but on a horizontal surface, that'll work out. And the frictional force ends up being proportional to this. Now, you can increase the normal force by piling a bunch of extra weight on top of this mass. And so then you'll actually end up with an additional downward force on the mass, but the normal force has to support all of the weight that you've got here. This is the principle behind the bags of sand that you stick in the back of a pickup in the wintertime. You effectively increase the weight of the object, which increases the normal force. And because the frictional force is proportional to the normal force, you get more friction between your tires and the road by piling that sand in there. And so you can stop better and start better by increasing that frictional force. So that's the idea behind that. Now, the proportionality constant that we use for friction is an odd one. It's we use a Greek letter. It looks like a U that's got a tail on each side, and this is the Greek letter mu. And it's spelled MU, if I remember right. And it's also the metric prefix for micro. So if you see something like, let's see, maybe a wire diameter is, this would be a really thin wire, but if it's something like 35 micrometers, okay, that would be 35 millionths of a meter. And as a Greek prefix, it means 10 to the minus 6. So that's a millionth. But in the context of friction, it doesn't mean that, but that's just someplace else that you might see that symbol anyway. But the frictional force, it actually takes on two natures. One of the natures is if you're trying to get an object moving that is at rest, you can push on it a little bit and it doesn't go anywhere. The amount of push that I'm giving it is matched by the frictional force, so it goes nowhere. And I can push a little harder, still doesn't go anywhere, still doesn't go anywhere until finally it does move. Okay, that's called static friction. And that's when the two surfaces are not moving with respect to each other, they're locked together. So surfaces locked together that's static friction. And for static friction, we just put a little subscript on the mu and call it mu sub s for static friction. And the static frictional force is less than or equal to mu sub s times the normal force. Now, that less than or equal to means it has a maximum value of mu sub s times n, but it can be less than that. And it's that maximum value that you have to overcome to actually get something to move. If you're just pushing on it not enough, the static frictional force will just increase in strength until it reaches that maximum value, and then it'll break free. I don't know that anyone has ever looked up the coefficient of frictions or experimented to find this out. The coefficients of friction for a Texas Instruments TI-36X Pro on paper before, that would be something you'd have to do by experiment. And by the way, that's how we figure out coefficients of friction, is by experiment. You can't predict it theoretically, you just have to experiment. And it ends up depending on all kinds of things. It'll depend on the humidity. It'll depend on the temperature. And so the best you can do is just come up with an estimate of it, and that's what we'll get. So when frictions are locked together, you have static friction, and most of the problems we'll be interested in the situation where you've maxed out the static friction, like how fast can you go without skidding on a turn? Okay, well, you set the frictional force equal to this, and if you try to exceed that, then you're going to skid. And so that's something that happens. There is something kind of unusual that shows up with static friction. It turns out when you have a rolling object, the point of the rolling object that's contacting the surface is instantaneously at rest with respect to that surface. And so rolling motion uses static friction. It's when the thing locks up and you start to slide that you begin to use the other kind of friction. So that's an important point. Rolling, if it's pure rolling, uses static friction. Okay, so that's something. And then if you have the surfaces sliding past each other, this would be like skidding your tires. So that's called kinetic friction. And for kinetic friction, we just use a subscript of k on the little Greek letter mu. So mu sub k And we usually use lowercase f's for friction. The kinetic frictional force is just equal to mu sub k times n. Once you've got those bumps sliding past each other, they don't get locked up again. And so we have that going on. Now, what did I do with the problems? Oh, I printed them. There they are. That I was going to do today. Oh, I wanted to show you before I started doing problems. This is a table that I got out of some book or another. I don't remember which one, but it shows the coefficients of friction between different objects. And this column here is the static friction, and then this column over here is the kinetic friction. And I don't have them all. Usually, oh, Teflon on Teflon. That's a pretty low one. Teflon is that surface that they put on fry pans. That it's the non-stick surface. So it's mostly non-stick. As the pan gets older, the Teflon gets worn off and presumably shows up in your food, although maybe most of it comes off when it's being scrubbed or something like that. But it may be something that you're eating unaware of. But Teflon has quite a low coefficient of friction. You can actually buy sheets of Teflon, and sometimes they call it ultra high molecular weight plastic. And I've bought some before. I've bought pieces of it that are like 8 inches wide and 4 feet long. And I'll use it for different projects. I've made a lot of tripods and various types of observing equipment where I would have a Teflon bearing between two things so it could move easily for realignment, and takes advantage of that. At school, we have a very large Newtonian telescope, and it's actually got a mirror in it that is 18 inches in diameter and about that thick. The mirror by itself weighs about 50 pounds, and it's in a huge tube that's big enough to house the mirror in, that's almost 8 feet high. And it's very heavy, but it's built in such a way that you can change the aim of it with one hand just by tilting it on the thing. It's very well balanced, but the contact point is Teflon with plastic laminate, sliding on plastic laminate, and it moves very easily. So that's something kind of nice. For the most part, when you look at things like steel on steel, this would be like train car wheels on iron rails would be pretty close to this. So 0.74, that's the coefficient of static friction. By the way, coefficients of friction are dimensionless. So if you remember, the static frictional force is equal to that, or less than or equal to this mu sub s times n. This will be measured in newtons. This will be measured in newtons. So you've got newtons on one side, newtons on the other. You can't introduce any other units or you couldn't have an equality. So that's why these things are dimensionless. But you may notice that the static frictional coefficient here is bigger than the kinetic frictional coefficient. That's usually the case. Same with aluminum on steel. Static is greater than kinetic. Copper on steel. Static kinetic friction is bigger, and that's the case with almost all of these things. About the only ones that isn't the case with is the Teflon on Teflon and Teflon on steel. It keeps a pretty low coefficient of friction no matter what you do. So have that going on there. Let's see, rubber on concrete and rubber on concrete wet. Okay, that's tires, road or car tires on roads. That's something that you want to keep in mind all the time. Then it's got things like waxed wood on wet snow. Okay, used to be skis were waxed wood, and so you'd want that to be the consideration with something like that. Um, Metal on metal lubricated, that would be a layer of oil between the two things. So quite a bit higher. It's actually 0.15 is 2.5 times as high as 0.06. So when you have that oiled metal sliding past oiled metal, when it's sliding, that's kinetic friction. They move very easily. Ice on ice, it can get kind of locked up together if it's static friction, but once it's sliding, it slides very well. Synovial joints in humans, very low coefficient of kinetic friction. And so they slide very easily past each other. You want that to be the case. You don't want your joints grinding when you're bending your elbow or your knees or something like that. That leads to medical problems. So those are just some examples. You don't have to memorize these or anything, but keep in mind that most of the time the coefficient of static friction is going to be greater than the coefficient of kinetic friction. So, and we'll do various example problems for these things. So here's a question I'm sure everyone has asked themselves. If the coefficient of static friction between an oiled non-stick fry pan and a frying egg is 0.040, what's the maximum angle at which you can tilt the pan before the egg starts to slide? Well, this is going to be a new kind of problem. Let's see. Well, let's draw the picture here. And when it's asking for the maximum angle, if it's not sliding, then we're using static friction. And if we're interested in the maximum angle we can tilt this thing at, what we want to do is what I say call max out the static friction. In other words, we want the static friction, that force, to be equaling mu sub s times n. Now, this is just the magnitude of the force. They actually point in different directions, so we have to take that into account. So let's draw a free body diagram for this situation. We'll have this egg that's sitting in here, and I've way exaggerated the angle that will be necessary here, but we've got somebody's frying a sunny side egg up there, and that's what that thing represents. So forces on the egg. It's on Earth, so one of the forces is going to be mg. And then something I do on free body diagrams is when I've got a tilted surface, I'll draw a dashed line that's horizontal, and then I'll draw a dashed line that represents the tilt of the surface, and I've exaggerated it again. By even more this time, I think, but that'll be the tilt of the fry pan, and that's the thing that we're actually after. Now, the egg is sitting there on the fry pan. Another force that acts is the normal force, and normal forces are perpendicular to the surface. So even when the surface is at a tilt, that force will be perpendicular to it. It's not vertical anymore. And so the normal force will not equal the weight when you've got a tilted surface. So that's something new. I don't think we've done a problem like that before. Now, what about the frictional force, the direction of it? Well, it opposes the sliding. If the egg's going to slide, it's going to slide that way. The frictional force points in the opposite direction. And so it's going to be in this direction. Looks like that. It'll be the static frictional force. So a question I've asked on tests, not in this class, but in my engineering physics class, I'll just have an expression that looks like this. F sub s equals mu sub s times n. And the question will be, what's wrong with that expression? And what's wrong with that expression is this. These are vectors here. You cannot have this vector equaling this vector because they point at right angles to each other. And so if you have an expression that says one vector is equal to another one, that means they have the same magnitude and they both point in the same direction. This expression is correct. The static frictional force will equal mu sub s times n when the static force is maxed out, but this expression is not. So, because they point two different directions. They're perpendicular to each other, actually. So there's my expression. Now, it turns out the easy way to do this problem is to draw a picture. We're maxing out the friction. If we increase the tilt just a smidgen beyond that, then the egg slides down the pan and we go from static friction to kinetic friction. But we're maxing out the friction. So these three forces add to zero. And the way you add vectors is to draw one vector, draw another vector, draw the third vector, and every time you come to the arrow end of one vector, that's when you start the next vector. So I'll show you how to draw the picture for that. Well, the mg is just going to point straight down on my picture. And so there's the mg part. I have that. The f sub s makes an angle with that. And here I have to be a little bit careful about how I do my diagram. F sub s and n are perpendicular to each other, and they have to come back to the starting point of this thing because here's what I have. The sum of these forces is equal to 0, whoops, plus F sub s plus n plus F sub s plus mg is equal to 0. I have a dying pin here, but hope you can still read that. Anyway, these three have to add to 0, which means when I go around this force triangle that I'm drawing, I'm going to have to come back to 0, but I have to make sure that my arrows for the static frictional force and the normal force take on approximately those directions, but they have to be perpendicular. And what that means is this angle has to be a right angle. So this is my F sub s right there. Here's my N. And then let's see, which one of these angles is going to be my theta angle? Oh, I could do it down here. This is theta here. Okay. This would actually be a right angle, which means this is going to be 90 minus theta. And in a right triangle, this angle and this one have to add up to 90 degrees. So if this one's 90 minus theta, this one has to be theta so that this angle plus this one equals 90 degrees. The three angles in a right triangle, in any triangle, add up to 180 degrees. And if you already have one 90-degree angle in them, then the other two have to add up to just 90 degrees. So that's how I know that this is 90 minus theta and this is theta. And I look at this, the side opposite that angle theta is F sub s. So F sub s is side opposite theta. N is the side adjacent to theta. And so F sub s divided by N is going to equal the tangent of theta. That's the opposite over the adjacent. But F sub s is equal to mu sub s times N. So that means what I have is mu sub s times n divided by n is equal to the tangent of theta. The n's divide out, and mu sub s is equal to the tangent of theta. So that's the way I can figure out the angle. Now, anytime you have this being the case, that means that theta is the inverse tangent of mu sub s. That's something that I haven't really taught you yet, but if you've had trigonometry, the sine, cosine, tangent stuff in a class, you've used that. And the way you denote it is you put a -1 up here. Now, in this context, that -1 is not an exponent. Usually, if you've got x to the -1, that means 1 divided by x. But when it's a function like this, which is what the tangent is, that -1 up there means the inverse tangent. And when I took trigonometry in high school, I may have mentioned this, I don't remember, but I was using this book that it was a programmed instruction book, and it would start off with just a page or two of example problems and explanation. And then there'd be some problems to do based on just a few ideas they'd just given you. And then they'd have another couple of pages of examples and explanation and more example or more problems that you did based on that. And it was broke it up into really small chunks. And I very much like doing that. You could teach it to yourself, and that's what I ended up doing, actually. So something I learned when you wrote an expression like this is that when you see this, and actually another notation for that would be theta is the, you may see the arc tangent of, whoops, mu sub s is what's supposed to go in there. The arc tangent, the way you read this, or the way that I read this to this day, it's the angle for which the tangent is mu sub s. Well, mu sub s is just the number, but if I think of it that way, it's the angle for which the tangent is a particular numerical value. Then what you get when you evaluate this is theta. And on my calculator, I really like it because to put in the inverse tangent, I don't have to hit the second button on this one. I just push the tangent button twice. And I don't know if you can see that or not, but it has that 10 to the -1. Now I just put in the coefficient of friction here, 0.040, close off my parentheses, and I get an angle of 2.3 degrees. So I'll go with that. So in this case, theta is the, equals tangent, inverse tangent of 0.040, which has two significant figures. The 4 here is significant, and the 0 after it is. The leading 0 is not. But I get 2.3 degrees. So all kinds of new stuff on this problem. One thing was a tilted frying pan. Another was this introduction of friction. And then drawing a force triangle. That's something you can do sometimes on these Newton's law problems. If you have a vector expression that has only 3 vectors in it, you can draw a triangle to solve that. Now, it's not always a nice triangle. Sometimes it's less work to do other things, but you can do that, but only if you have a 3-vector problem. That means 3 forces and 0 for the acceleration. And what this means, this expression means F net equals MA is equal to 0 when those 3 add together. So you can have 3 forces adding to 0, or you can have 2 forces acting on something equaling an acceleration. And that's a 3-vector problem as well. So, but then we also had the inverse tangent function. So lots of new stuff on one problem. Let's see one that maybe doesn't have an angle in it and see what we can do in that case. Okay, it says the approximate value for the coefficient of static friction between worn tires and a road is 0.30. I mentioned that a rolling tire has static friction and a skidding tire has kinetic friction. I don't know if you've ever explored the anti-lock brakes of your car or not, or maybe you have a car that doesn't have them. When I was in learning to drive, there were no such thing as anti-lock brakes. And a phrase that we learned when we were driving, especially in the wintertime, was to pump your brakes. And what they mean by that is you push on the brake and then you let up, and you push on the brake and let up. And what that does is if you just push on the brake too hard, you lock your wheels and your tire is sliding over the icy surface you're on, and you'll stop in a much longer distance because kinetic friction is less than static friction. Now, the anti-lock brakes, the way they work is they've got an electronic sensor in the wheels. Maybe, I don't know how many of the wheels they put them in, but as soon as they sense that the wheel is about to lock up, they'll back off on the brake pressure so that the wheel continues to roll and keeps using static friction. And if you push hard on your brakes when you're coming to a stop, you'll feel this kind of vibrating motion. That's the brakes applying and backing off and applying and backing up, off and applying and backing off. And the electronic anti-lock brakes can do it much more intelligently than a human does when they're pumping the brakes. And so they're a good safety feature for stopping better. But we'll just pretend that this car is, the driver is braking gently, so he's maxing out the static friction, but not actually skidding. So we want to stop this car, and the car is going 70 miles per hour at first. That's not going to help us, so our first task is to convert that into meters per second. 70.0 miles per hour, and I multiply by 1 mile is 1,609 meters. I'm about tired of that pen. I think this one may work better. Whoops. That's a Sadie hair. That's our dog. That many meters in a mile. And so you can see our miles are going to go away. And then I want to convert hours to seconds. The hours are on the bottom, so I stick it up here. And there are 3,600 seconds in an hour, 60 minutes, and each minute has 60 seconds. And it's just a number I remember. So that'll be some number of meters per second. So 70 times 1,609 divided by 3,600. And I get 31.3 meters per second. So I'm not going to draw a picture on this, but otherwise I'm going to proceed with my, or I could draw a picture, actually. Doesn't take me long to draw a car, at least not the way I draw cars. So there's our car. Looks like a, who knows what. Anyway, down here I've got static friction. So I'm just going to put a little mu sub s there. And the car is initially going at some speed v. We want to know how long will it travel before it stops. Well, if I know the initial speed, and I know, what do I know? I'll know the frictional force. I'll be able to figure out the acceleration, and I don't care how long it takes in time to stop. I just want to know how far. I may be using that equation that doesn't have time in it. So let's see where that gets us. Now, there's my sketch. Next thing I've got to have on a Newton's law problem is a free body diagram. And so here we go. Okay, one of the forces that will be acting is mg, downward. Another force that'll be acting is the normal force, upward. Okay? And in the vertical direction, there's nothing going on. Okay, the car doesn't fall through the road and the car doesn't jump off the road. So that's something. Then I've got friction acting. It's not just those two forces. So the friction, if the car is going that way, it's the force that has to stop the car. So it's going to be pointing opposite the direction of the car's motion. And so there's that. And so in this case, it'll be static friction. So it'll point that way. Now, a way that I solve these problems is I introduce a coordinate system a lot of times, and usually I'll have X go that way and Y go that way. When we get to inclined planes, sometimes I'll rotate this coordinate system. It'll be nicer. But then I'll start off by writing Newton's second law in vector form. And what I mean by that is that I just do this. I'll go F sub S plus N plus mg. Those are the three forces acting. When you add them together, you get the net force. So that'll be my F net, and that'll equal the mass times the acceleration that I have here. So another way I can write that is over here I can put the sum of the forces is equal to this plus this plus this, and that's that symbol that means sum of. So that's what I have. Then I look at the situation I've got, and one thing I can say is I'll write this. The sum of the forces in the y direction are going to equal 0. There's nothing going on in the y direction, and so what I know from that is that the ones that are acting in the y direction, either up or down, that's n and mg. Those two add to 0. And because the car isn't falling through the road and it's not jumping off the road. So I know those forces have to add to 0. And so what's left is the sum of the forces in the x direction. Now that's still a vector equation, but I could just as well write, no vectors. I could go n minus mg is equal to 0. This is a scalar equation. And actually, I wrote this as a scalar equation. I probably wouldn't have done that. But anyway, that tells me something about the normal force. It'll equal mg. But in the x direction, the sum of the forces in the x direction, that's going to equal ma. That's where the acceleration is, in the horizontal direction. And what I see is that frictional force is pointing in the minus x direction. It's pointing to the left. That's the negative. And so what I have for the sum of the forces in the x direction is just that one force, and it'll be minus F sub s equals ma. Now that static frictional force is equal to mu sub s times n, but n is equal to mg. And so I can say this, the static frictional force in magnitude is mu sub s n, but n is mg, so it's mu sub s mg. So I've got this series of steps that I have to go through to figure out what the static frictional force happens to be. It's not always that nice. If we put this on a tilted and inclined plane, turns out the normal force is not equal to mg in that case. And that's what we'll do as a first problem tomorrow, probably. But we have that. So I can replace the F sub s here with mu sub s mg, and I get minus mu sub s mg is equal to ma, and I've got m's on both sides, and I can divide those out, and I'll get that the acceleration is minus mu sub s g. The minus sign tells me that it's opposite the positive x direction. So I want to know the shortest distance in which the car can stop. Well, we can figure that out now. We know the acceleration, we know the initial velocity, and I could call this v naught now if I wanted to. And an equation that uses those is this. V squared is equal to v naught squared plus 2a times x minus x naught. And I'm just going to call this delta x. That's the change in the x position. And we're bringing the car to a stop. And so this v is going to be 0. And so I'll have 0 is equal to v naught squared minus 2 mu sub s g, 2a, and a is that, and that's the minus sign, 2 mu sub s g delta x. Okay, well, I can solve this now. Let's see, I may do something to bring in a piece of scratch paper so I can keep going on the same line or the same direction. 2 mu sub s g delta x is equal to v naught squared, or delta x will equal v naught squared over 2 mu sub s g. Now that's kind of a handy expression, but it tells me a few things. One, the smaller mu sub s is, the bigger delta x is going to be. Small mu sub x means slick surfaces. Okay, so if you're on ice, it's going to take you a lot longer to stop. Also, the distance it takes to stop goes up with the square of the speed. So if you're going at 60 miles an hour, as compared to 30 miles an hour, at 60 miles an hour, it will take you 4 times as long to stop, or 4 times the distance to stop. So in the winter, slow down if it's on a slick surface, because it's going to take a while to stop. But now we can finally plug in the numbers. Delta x in this case will equal v naught. We figured it out up here. That's the 31.3 meters per second. So, and I have to square that, and I divide by 2 times mu sub s was 0.30 times g, 9.81 meters per second squared. Okay, to check my units, on top, I'm going to have meters squared per second squared. On the bottom, I will have meters per second squared. And when you divide a fraction by a fraction, or just divide by a fraction, you bring it up and flip it upside down. So I'll have seconds squared per meter when I divide by that. And the seconds squared divide out, and I'll have meters squared over meters, which is just plain meters. So that's what I expect for a distance. Let's figure it out. 30, I still got that saved in my calculator, so I can just hit the squared button, divided by 2 times 0.3 times 9.81. And I get 170 meters. I've only got 2 significant figures here. So delta x equals 170 meters. And if you multiply that by 3.28 feet per meter, just to figure something out here, you get about 550 feet. That's a long ways. That's almost 2 football fields long. So Drive carefully. Now, if I go back to my, whatever I put that sheet, here's the one that had rubber on concrete dry. The coefficient of static friction is 1.0. This is for new good tires. If you have worn tires, the coefficient of friction between them and the road drops to about what it is for rubber on wet concrete instead. And so, let's see, I don't have rubber on ice, but it's smaller still. So, gotta be careful driving. Okay, we did a couple of fairly challenging problems today. Check out some in the textbook. Let's see, and practice this stuff. I'll be able to get some stuff pointed or posted here today. Something I'm going to let you do is do a makeup test for number 1, and what you'll actually do is treat it like a homework assignment, and you'll be able to print it off, solve the problems on the test, convert it into a multi-page PDF. And by the way, there's a PDF assignment on our Canvas page. Check that out. I want you to master the art of making a multi-page PDF, because I've really got some headaches that I still have to deal with when people can't do that very well. And so there's that assignment too, and it's fairly simple, but do that. But anyway, practice some problems, and I'll post that makeup test assignment here sometime this afternoon or evening, and you'll be able to work on that. And what you can do with that then is, I don't remember how many points there were on the test actually, maybe 95. And you haven't even seen your test yet. Yeah, I need to be getting those back. But say you got 60 out of 95 on the test. If you just do the problems that you didn't get full credit for on the test, and then your score on those problems will be the average of what you got the first time and what you get the second time. So basically it lets you cut the distance between your score and a perfect score in half. And so it'll give you some help in that regard. And it'll also help prepare you for the final test, because some of this stuff is going to show up on the final test again. A sampling of it will. So we'll have that going as well. But other than that, I'll stop here and turn you loose for the rest of the day, and I'll get going on some of these assignments that I have to do.
Oh,
Okay.
Mr. Ham,
Yes, Ben.
sapling question 11 yesterday that you were talking about doing an example problem like that today.
Oh, shoot, I didn't get to it. Yeah, I think that was the next example problem. Was that the one with a tilt?
Yeah, it's the one with the 2 Atwood machines.
Well, the Atwood's machine I did a couple days ago, if it was just the Atwood's machine.
I think it's like Atwood's at an angle though, and there's some like other stuff in there.
Oh,
like
okay. Oh, there's a pulley. Yeah,
Yeah.
there's a pulley and 2 things at an angle. I may save that problem and stick it on the next assignment. Okay, I can never remember my sapling login. And it's one they gave me, and it's really easy, but okay. All right. Yeah, I'm going to take that problem off and stick it on the next assignment, because it would be a good one for the next assignment. But I have to look at it first. Oh, two connected blocks, right? I'm pretty sure. Oh, you can't see. Share screen again. Go back to screen 2. Does that look like it?
Yeah.
Okay. I'm going to take that off there and save it for the next assignment because we haven't quite done anything like that. Oh, friction can be ignored. So at least there's no friction, but still it's a bit challenging. So yeah, we'll deal with that later. All righty. That'll please you, I guess. The rest of them, I think, should be doable. So we'll stop there. And I'll see you tomorrow.